गया होगा क्या?
Sir, he's sharing the slide right now.
Yeah, that's okay.
Can you see my slide?
Yeah,
Yes, sir. We can see your slide. We can see your slide.
Okay. Full screen करूँ भाई तो F5 के
Yes, sir.
full screen.
Tushar bhai, you see the slides all right?
Yes, sir. I can see the slides. We can see the slide, and it is full screen right now.
It is full screen. That's how I should keep, right?
Yes, sir. It is okay.
Tushar, you can go ahead. It's all participants are.
Okay. Joshi sir, we will proceed. Hello.
Hello.
Sir, I will start the session now.
Yes.
Okay. Hello. Can you hear me?
Yeah.
Yeah. Okay.
Yes.
Hello, everybody, and good morning to all of you. We welcome to the webinar series on the century of quantum mechanics and still going strong, which is jointly organized by Applied Physics Department, Faculty of Technology and Engineering, MS University, Indian Physics Association, Baroda Chapter, Gujarat Science Academy, National Academy of Sciences, Delhi Chapter, and Indian Association of Physics Teachers, Regional Council, RC7. Friends, today is the second day of our webinar series, and our eminent speaker for the first session is Professor Pankaj Joshi sir. Before we invite him for his presentation, it is my great pleasure, and I'm really honored to introduce an eminent physicist. Friends, Professor Pankaj Joshi is an internationally renowned eminent scientist. He was a senior professor in the Department of Astronomy and Astrophysics at the Tata Institute of Fundamental Research, TIFR, Mumbai. Presently, he is a provost of Charotar University of Science and Technology, Charusak, and the founding director of the International Center of Cosmology, which we say ICC. Friend, he is regarded as a scholar, physicist, and an expert on cosmology. I'm very happy to inform you that Professor Joshi is the president of Gujarat Science Academy. Under his supervision, we are working to upgrade the quality of science education in our state and to develop a scientific temper among the students. Professor Joshi's research interests are general relativity and cosmology. He has made a fundamental contribution in black hole physics and gravitational theory. His extensive analysis of general relativistic gravitational collapse has been widely recognized as providing significant insight into the final fate of a massive collapsing star in the universe, formation of space-time singularities, and cosmic censorship. His research, which mainly revolves around cosmology and gravitation physics, has been reported in more than 200 research papers in International Journal of Repute and also in monogram from Oxford University Press and a Cambridge University Press and other books. He has guided 13 students for the PhD and 10 postdoctoral fellows have worked under his advice. Friends, he has held a visiting faculty position in several countries, doing research and lecturing on this topic, and has won several awards as well as fellowship to scientific academics. He has been an adjunct family fellow and a visiting scientist to a Cambridge University, United Kingdom, Harvard University, USA, New York University, USA, University of Pittsburgh, Osaka City University, Japan, University of Natal, South Africa, and Queen Mary Westfield colleges. Friend, he has contributed a large number of books and articles towards science outreach and has given many public lectures, newspaper articles, and TV appearances towards the popularization of science and cosmology. Dear student, he has been awarded with many popular awards and prizes. Some of these are the Gravity Research Foundation USA Award for research work on the final fate of a gravitational collapse, Professor A.C. Banerjee Gold Medal and a Memorial Lecture Award by the National Academy of Sciences, C.V. Raman Lecture Award by the Department of Atomic Energy. He is also an elected fellow of the Indian National Academy, INSA, and National Academy of Sciences, and others also. Friends, there is a long list of his academic and administrative achievements. It is very difficult to cover at this stage. Really, we are fortunate that Professor Joshi is being with us online. With this brief introduction, I will invite and request Professor Joshi sir for his talk, sir. Over to Joshi sir. Thank you, sir.
Thank you, Professor Tushar Pandya ji. It's my great pleasure to meet all of you from a distance, though Professor Lokanathan was mentioning about how it feels meeting face to face versus on internet. But I think this is a very good medium and we can have a wide reach. These are the advantages. Can you see my slides or I should share the screen again?
Now, sir, you have to share the screen again.
Okay, I am doing it. Can you see the slides now?
Yes, sir.
Very good. So today, after the wonderful talks of Professor Ghatak and Professor Lokanathan, we are going to, go further in our journey. And I will talk to you about what I would call, or what, people like Stephen Hawking and John Wheeler and others have called quantum cosmology. The main key point is the following. See, yesterday in this wonderful lectures, we heard a lot about quantum mechanics, its origin, and then also it was alluded what great strengths the quantum mechanics has, and also some of its limitations. Limitations are mainly by way of our understanding of the, the quantum phenomena as a theory. As per my own humble understanding, you see, while it is great as a mechanics and with enormous applicability as a theory, as was pointed out, you see the name of David Bohm and others were taken. As a theory, there are ambiguities or interpretation problems as far as the entire quantum phenomena is concerned. No doubt, in the micro world, it is immensely successful and we do many, many applications of quantum mechanics. But, you see, physicists are not entirely or completely happy with applications. That is, when you make one or the other tools and, you do remote sensing and other technologies and so on, that is good for the physicists, but that is not wonderful for physicists. What they want is, you see, a unified view of cosmos. They want to understand universe more and more. They want to understand the universe in its entirety. And, they want a unified vision. So, on one hand, you have quantum mechanics, as was developing, as we are saying, 100 years of the quantum mechanics and so on. On one hand, we have the quantum mechanics, but on the other hand, you also have the special theory of relativity. Classical mechanics is in a way contained in quantum mechanics, but special relativity is, you see, another fundamental theory of nature. So you want your quantum mechanics to conform or, to be unified with special relativity. So we have then what is called a relativistic quantum mechanics, or sometimes also what is called quantum field theory. But then you go further. You have the general theory of relativity, the force of gravity, a very fundamental force in nature. And we know very well now that the Newtonian gravity by itself is not enough, is not adequate to describe the phenomena related to the force of gravity. So you have general relativity of Einstein, and now what you want is, you want the quantum mechanics and general relativity to be in one single framework again. Now, this is the great problem of quantum gravity. What I am trying to tell you right now is that even today, yesterday it was pointed out that, the problems with the interpretation of the quantum theory, the quantum mechanics, various phenomena, so on and so forth. But leave that apart. If you talk of the fundamental forces in nature, then you want the gravity and the quantum to be described in one single framework. So, what you want to talk about really is, so to say, the quantum cosmos. The universe, when you look at it in a very large scale, is, you see, governed by the force of gravity mainly. Now, on the other hand, the quantum phenomena, the quantum theory, as a fundamental theory of nature, you would expect that to play a very basic role in the governing global dynamics of the universe as a whole. And this is where what I call the quantum cosmology, that framework is needed. Now, of course, this is far from complete. The problem is closely intertwined with that of a possible quantum gravity theory itself, as I was telling you. And the very important thing is, very frontier developments, research developments in the fundamental physics and cosmology are happening here. So that is why it should be quite an exciting field to talk about and to have a glimpse when we are talking of 100 years of quantum theory. You see, I partly told you this, But then let me repeat, there are, four fundamental forces of nature as we physicists, talk about them in the current decades. So one is, of course, electromagnetism, the Faraday and Maxwell work and the theories. But then the quantum theory, the quantum mechanics came, started describing the, atom, the nucleus. When you, started probing the secrets of the atomic nucleus, then you realized that there are strong and weak nuclear forces. And of course, the fourth force, very fundamental force in the cosmos, is the gravity itself, which, as I was mentioning to you, governing the universe in its entirety on the large scale. Now the question is, can we unify them in a single theory of nature? Can we unify them in a single theory of physics? When it comes to electromagnetism and strong and weak nuclear forces, we have some kind of a theory, a very successful grand unified theory, as it is called. And that is the story of, particle physics and the Higgs boson, which this Large Hadron Collider was talking about and discussing, and so on and so forth. However, when it comes to uniting the force of gravity with the quantum phenomena in nature, there is a very big gap, very big vacuum, long way to cover. We are no way close to the, what I would call Einstein's dream. For past, many decades of his life, Einstein kept, making an effort towards a unified theory of nature. He made wonderful, efforts. Sometimes he himself felt he's very close. I mean, that was his dream, you see. He always talked like that, oh, these numbers, you see, what is the value of the constant G and C? These are all details. I want to see the, the real design by the God. That is what, he always talked about. So for him, a person like him, applications of quantum mechanics and all that will not give him joy. I mean, it's okay, he will use it wherever necessary. But, his dream, as we would call it, is the unified theory of nature. And that is where there's a very huge gap. I will try to give you today, what is the key reason for this such a big gap in our efforts, to unify these theories of nature on one hand, and on the other hand, then I will try to tell you some frontier developments in research in astrophysics and cosmology, where our, a cosmology center is also working here at the Charusat University. So I'll try to give you a little bit of glimpse of that also, but mainly I'll try to highlight the research frontier where, the action is taking place. All right, in order to do that, first, let us talk about the general relativity, or what is also called the Einstein gravity. Almost 100 years, or I think a few more years have passed since Einstein developed his equations of gravitation, which are called, famously called Einstein equations. 1915, he developed those equations, the general theory of relativity. Now, this has found enormous applications. You don't see one single day where there is no report in one or the other newspaper on black holes. They have fascinated the, what shall I say, not the universe, but at least the human population in a very big way. Only today I saw a report. Some poetry is always mixed, you see, whenever they discuss of black holes. So this report says that, a black hole is, you see, throbbing like the heart, human heart at the center of the universe. Now, this is very interesting to a common man, you see. Forget the science and forget the gravity and then Einstein is, you see, another, well-known famous name. Now, all these things have a scientific background, but what I'm trying to tell you is that the Einstein theory of gravity has, you see, led us to, the black holes, and then the origin of the universe, the Big Bang, and then very recently, we have been reading a lot. The Nobel Prize of 2017, I think, was on gravitational waves. Then, almost going back to our, Puranas, not just one universe, but there are multiverses. And then, can we go from one universe to the other? I mean, this is almost like the epic travels of some of the, some of the beings which are not human beings, but which have extra powers, which are discussed in, I think, some of our ancient texts. But the scientists are discussing today in all seriousness the multiverses. Then there are time warps or time travel. And the very exciting feature on which I'll, pay some more attention today is the space-time singularities. What I'm going to tell you is that the space-time singularities may encode the secrets of quantum gravity. And then when they are actually visible to us, sometimes called naked singularities. So how all these things are related to our, future quantum theory of gravity or the Einstein's dream, I'll try to tell you while relating it with the, some of the phenomena of quantum gravitational nature, where a lot of work is happening. But the key point here is that the usual quantum mechanics is just in Euclidean geometric framework. Please understand this very carefully. And I am subject to correction by, the eminent scientists present here. But it is just 3 dimensions of space and 1 dimension of time. That is what the Schrödinger equation or the usual quantum mechanics talked about. But when we talk of gravity, the fundamental change that Einstein brought in was the geometry of space and time. Einstein said that we must move beyond the Euclidean geometry. We might be very successful locally. Okay. I mean, the surface of the earth also looks flat locally. But when you look at a global level, go out there in the skies and you see the curvature of the earth, locally you don't see it. Locally you measure out everything as if, everything is a flat 2-dimensional Euclidean surface. But on a global scale, you see that actually it's a sphere. So similarly, Einstein distinguished, and this is the very, very important fundamental point, of the general theory of relativity. What? That the local geometry is flat, but globally, on larger scale, when you go, it's a curved space-time continuum. So, if two ants were walking on a flat surface in a parallel way, जैसे कहते हैं ना कि अपनी नाक की डांडी पे चले जाओ नजर सीधी रख के parallel, so they will never meet. But then if the surface was different, suppose the surface was that of a sphere, then even if they were walking in a complete straight line according to each of them, they will end up meeting each other, whether they want it or not. So social distancing will be violated. On the other hand, if you were on a saddle surface, okay, वो जो horse का होता है ना, saddle डालते हैं, पलाण घोड़ा. So there, if you are on that surface, the ants keep walking in the straight line, then they will keep moving away from each other. So these are all three different geometries. So the heart of the Einstein's theory of relativity is that the objects in the universe will curve the geometry of space and time in different ways, like these different surfaces. This is, you see, my one-line summary of Einstein theory of relativity. I'll show you some equations also a little later, but this is on a larger scale. When we go to a very small scale, you see there are two things. On large scale, there is universe, and then that is called your macrocosm. On the other hand, you have your microcosm, and microcosm is where the quantum mechanics is in full bloom, playing, you know, its huge influence. You need not worry about gravity, really, or so to say, need not worry about gravity. But the gravity enters in a different way, even at the microscopic levels. At usual levels of atoms and nuclei and so on, your flat space-time, Euclidean geometry, everything is okay. But when you go to smaller and smaller and smaller, length scales, and the smallest is what is called the Planck scale. It is obtained, by putting the fundamental constants of nature together, the Planck scale. When you come to the Planck scale, the actual space-time may not have a continuous nature. It would have a foam-like continuous, topological fluctuations in the geometry of the space-time. And this is where the physicists are trying to formulate their quantum theories of gravities. More on that later, but let me tell you now, the most brilliant minds in the universities and research institutes today are trying, today to formulate, as I was telling here, unifying the single theory of physics. So some of these major efforts are string theory, for example. Okay, then another one is loop quantum gravity. Another is quantization in a curved background. And this is where the well-known Hawking radiation is also, coming into picture. I hope so far I am quite clear. You see, what did I say? What message did I drive so far? The message is the usual quantum mechanics is all right at the levels of atoms and microscopic levels, but it is using only 3+1 dimensional time and space. It is not including the curvature of space-time as implied by the Einstein theory of general relativity. Okay? So space-time curvature is not there. So the gravity and quantum remains separated. And they have maintained a great, wonderful social distancing, to use that word again. I mean, physicists have tried very, very hard to bring the two together. But God knows what kind of repulsive force. But now I gave you an idea of what that repulsive force is. The Einstein theory's mathematical framework is curvature of space and time. So that framework is very, very different from that of quantum mechanics. Quantum mechanics is flat Euclidean geometry. Einstein theory is the Riemannian geometry. You see, Bernard Riemann is a great mathematician, and it was the Riemannian geometry that Einstein used, the curvature of space and time. And as a result, the entire mathematical framework for general relativity or the Einstein gravity and the quantum mechanics are entirely separated from each other, and therefore there is no unification available so far. Now, the greatest attempts that have been made are the string theory, trying to bring quantum mechanics and gravity together, loop quantum gravity, quantization in curved background, and Hawking radiation, on which you might have heard from black holes. That is related with this quantization in the curved background. But to give you a summary, really string theory is a misnomer. There are, various attempts, there are various mathematical frameworks, but we don't have a single theory. That was the purpose really of the, string efforts. I remember actually, you see, my meeting Professor Stephen Hawking in his office in Cambridge University. And at that time, the big volumes, you see, 3 volumes of Green, Michael Green, Schwartz, and Witten, Edward Witten, they had come out, string theories. So Stephen Hawking told me his office was located just above the Cambridge University press offices. So he just told me, you see, as a young physicist, I was talking to him for his advice. He just told me, just go downstairs. The string theory volumes have just come out. Just study them. You will make a name for yourself. But I am, you see, sort of a little intrigued or somewhat disappointed to report to you that we have not reached really with the goal of uniting the gravity and quantum. The best of the minds in the Princeton, Harvard, Caltech, the theoreticians work so hard for string theory. Not much has come out. Then the loop quantum gravity is the effort by Abhay Ashtekar, our own Indian physicist, though Indian American and settled in US at the Penn State University. Ashtekar pioneered this particular approach. Again, severe limitations have been discovered. Unfortunately, we haven't made a big, breakthrough. Quantization in curved background. You see, this is a very big, difficult subject because flat background, quantum mechanics is there, quantum field theory is there. But when you have a curved background like that of, you see, the outer side of a star, it's a curved geometry, exterior of a sun or a massive star. It's a curved background. It is not a flat background. How will you quantize? How will you understand the physical processes, the particle collisions, colliders? How will you understand it there? So they developed a theory, but again, it was an ad hoc theory. But then there is a lot of discussion on Hawking radiation. Now, as I said, see, I am emphasizing, this because I am sure there are many young listeners. There are, lots of students here listening to this talk. And what I want to tell them is what the research frontiers are. We have been told wonderfully well yesterday, the, key important features or the crux of the quantum mechanics. But now we go to the frontier. And then entire problem is we must quantize in a curved background. And then, there was a wonderful alluding to the Schrödinger equation yesterday by both Professor Lokanath and Professor Ghatak. Where did it come from? The Schrödinger equation. And the professor said that, well, it came from nowhere. You see, in a unique way, Schrödinger just wrote his equation. Now, the question is, can you write down, Schrödinger-like equation for a curved geometry and not a flat geometry? So that attempt was made by John Wheeler, Bryce DeWitt. Wheeler-DeWitt equation, a lot of discussion has been there, and together with that, the many worlds interpretation of quantum mechanics. There's a huge literature there. Right now, I'll just mention that. Again, we have not made, very big progress. We have run into formidable difficulties. As I already told, all the current quantum mechanics and quantum field theories are in flat Minkowski space-time. Enormous difficulties, no uniqueness, and therefore the issue of quantum gravity is, quite unresolved as of today. The string theorists, the loop quantum gravities, मतलब कहते हैं ना कि बहुत रनिंग किया, you see, I mean, the goal is not sin in the sight, and abhi now you need a new pathway, really. Now, I'll change a gear. I'll change the, my mode of my direction, really. What do? Matlab, difficulties are well known. You will see many review articles. If you, read any review article on string theory, on loop quantum gravity, on quantization in curved background, difficulties क्या है, तो बहुत रोना धोना आपको सब मिल जाएगा देखने को. You see, lot of crying is there, lot of, the वो कहते हैं ना कि failed attempts, you see, are lying everywhere, corpse. सब जगह पे आपको दिखाई देंगे. But the question is, what do you do? Where do you go? Is there a way out? And in fact, I am trying to, or I will try to propose some kind of, future direction, a future outline as to a possibility in the direction of quantum gravity. And that, I will say, is the secrets of, massive stars. There are large stars in the universe. big stars in the universe. They live their lives. And when they die, towards the end of their life cycle, you see, to my mind, the top secrets of the, quantum gravity must be, lying there. And I will try to give you an indication in the rest of the time, and that is available to me. I think I started at about 11 at 10, so maybe another 20 minutes or so I'll take. So what happens when a very large star dies? You see, stars live their lives fusing their internal nuclear fuel, hydrogen, for example, in the sun fuses to helium and other higher elements, finally iron, and then star starts cooling. The classic work of Chandrasekhar, the great Indian astrophysicist, lies there. He gave the theory of white dwarfs, and now the stars, if they are much bigger than the white dwarfs, then in that case, you are faced with a question as compared to sun, which has lived for some 5 billion years so far, and it has still to live another 5 billion more years before the pralay comes. Pralay in the sense of, sun's outer layers will expand when it cools down, and it will engulf the Earth and nearby planets. So it's the end of solar system. But still, for young students, I would say, don't worry, there are 5 billion more years to go. So you can make your, careers and your families, and you will see your grandchildren's also. No problem. But the thing is, the life of a star also comes to an end. That is the whole point. Bigger stars die much faster in a matter of few crores of years. What happens to them? That's the key question. And I will straight away go to the story now of black holes. This was first studied by Robert Oppenheimer and Schneider. I have skipped the stories of white dwarfs and the neutron stars in between because of lack of time. I am straight away coming to the story of black holes and that of space-time singularities, because that is more relevant to the topic today, and that of quantum cosmology and quantum gravity. Oppenheimer and Schneider studied the gravitational collapse of a very massive star in the universe. What they found was that the final fate of the star will be an object like this. An object which is, you say, schematically like this. There is an event horizon from which nothing will come out. At the center of black hole will be a space-time singularity, and then that is covered by what is called a photon sphere. So what you have is kind of black hole developing in the space-time. When a massive star, collapses gravitationally. You see in this figure on the other side, there is a three-dimensional picture. The star is shrinking, shrinking, shrinking. You see, the star is like a balloon. A balloon has the rubber pressing inwards, but the air inside is pressing outwards. There is a balance. But when I release the air, the rubber compresses and the balloon shrinks. Similarly, in a star, there is an inner pressure created by the nuclear fusion. But when that pressure subsides, the gravity compresses the very large star enormously. And a star which has lived millions of years will shrink to a very, very small size, that of a full stop at the end of a sentence within matters of few tens of seconds, that is in few minutes. So that is called a catastrophic gravitational collapse of a massive star. At the end of the collapse of the star forms, as I said, black hole as pointed out by the work of Oppenheimer and Schneider. But the Oppenheimer and Schneider work, the calculation that was done was way back in 1939. It had a lot of limitations. They had made a lot of assumptions, like the star is completely homogeneous, the star has no rotation, there is no internal pressure within the star. Now, all of these are not correct. The stars still have internal pressures. The stars do rotate. The stars are not entirely spherically symmetric, so on and so forth. So their calculation, which is, in terms of equations like this, is not entirely foolproof. In other words, it's a limited calculation. So what you really need to do is you need to make realistic calculations. Now, in some 15 minutes left to me, I may not be able to tell you all the calculation details, but I can tell you that it's very complicated to do calculations in general theory of relativity, because the Einstein equations themselves are second order, non-linear, partial differential equations. Now, I can tell you that when we started studying differential equations in our mathematical courses, immediately the students were scared. कि भाई ये algebra तो ठीक है, you see, solving an algebra equation and finding two equations and finding the values of x and y is okay. But ये differential equation क्या? You see, एक नया ghost आ गया है. अब वो differential equation में भी when it came to the partial differential equations, from ordinary differentiation to the PDEs, partial differential equations, already it got complicated. And then, as you all know, the PDEs are much difficult to solve as compared to ODEs. ODEs are ordinary differential equations. And then also when they are non-linear, okay, I will not define for you linearity and non-linearity, but most of you will know it. So they are too difficult to solve. So Einstein equations, solving them under realistic assumptions, that is why Oppenheimer and Schneider solved them in under a lot of assumptions. But this task was carried out by physicists, including my own work, work of our own students and postdocs and so on. And the conclusion is that sometimes the star collapse makes a black hole, but sometimes it makes a singularity only, and that singularity need not be within a black hole. If the time had permitted, I would have liked to tell you the intricacies of some of these equations, but the important point is that what you really do is you study the dynamics of this event horizon. Can you see the event horizon covering the singularity? At the center is the singularity, but there is an event horizon. This event horizon is the key word in black hole physics. So what we do really is by means of this kind of equations, we study the dynamics of the event horizon. And then what we find is that sometimes the singularity, which is, as shown by a curly line at the center of this figure, sometimes this, singularity is covered entirely within event horizon, but at other times it is not covered within the event horizon. So what that means, I think this figure should, give you the idea. What that means is that from the singularity itself, वो ब्लैक होल में क्या हो रहा था? ब्लैक होल में ये हो रहा था कि you have the singularity hidden within the center of the black hole, and nothing comes out of the black hole, so you don't see anything. But after very complicated calculations over past few decades, now physicists have found that from the very singularity, you can have the light rays and particles coming out. The black hole either does not form or it forms much later. And this is called the naked singularity. I'll skip these equations and these mathematical, details. But I'll tell you the picture, key picture. See the bottom of this particular figure. When you have a very large star, say 10 or 20 or 30 solar masses, two things happen. Depending on the initial conditions, these initial conditions are described in terms of, the parameter space, the velocities of the collapsing shells and the mass distribution and the density distribution. Here, we do not take the entire star to be homogeneous. The densities are higher at the center, as would be the case in, almost all realistic star collapses. So when you do that, either a black hole will form or there will be an exploding fireball, that is a singularity. Now, the very important point. What is the very important point? This singularity, near and close to the singularity, the densities, the temperatures, the space-time curvatures, all the physical quantities will be in their extreme. They are extraordinarily high. Unlike any densities you have seen. What densities we see? We see nuclear densities, we see plasma, but the neutron stars are much, much denser. Take one spoonful of a neutron star and weighs, is it tons and tons? But this is even higher densities than that. So, extreme densities in the vicinity of the space-time singularity, temperature, space-time curvatures, and so on. So, close to such a space-time singularity, the quantum gravity effects will be very, very important. The singularity is already close to the Planck scales. It is very small length scales. Very small length scales on one hand and very high gravity on the other hand. Please note these two things. I said extremely small length scales. So quantum mechanics must be very important. And extremely high gravities. So Einstein theory is very important. So close to a space-time singularity, what you have is the bubbling of quantum gravity. The real quantum gravity phenomena will be occurring in the vicinity. It's the dance of Shiva really happening over there. If you, allow me to, use little bit of a picture language. So huge debate, you see, internationally. Stephen Hawking said that only black holes will occur. Never the visible singularities will occur. Finally, he accepted one fine morning that yes, singularities, yes, the singularities without event horizons can happen. And that made a first page article in New York Times, you see. And then our work was, of course, there for decades. So I was asked by the well-known scientific American magazine to write a review on all these developments. And the bonus was that they splashed it as their international cover story, and they gave title Naked Singularities. This was translated in more than 20 international languages. Unfortunately, it is not there in Hindi or Gujarati, but I think it's okay. We, people in India have always great fancy for English language. So I think it is the PDF is available, or I can make it available, on the website of Gujarat Science Academy. And this review article is there. You can see. But to, come to the, later part of my talk, the black holes and singularity spacetimes have very distinct physical properties. Physicists have been, and astrophysicists have been exploring the, astrophysical signatures. And that includes, by the way, Stephen Hawking also. He also explored what happens in the vicinity of singularities. But in a collaboration with the Harvard University, we, wrote a research paper which is very widely cited. We showed that, when you are in the vicinity of a singularity, the radiations that come out from that region in the sky are in extraordinary high frequencies, which are never seen in a black hole case. Now, what does this mean? See, at the end of the day, an astronomer is going to ask me, कि बाबा आपने सब ये theory बना लिया, singularity और black hole and relativity, ये सब हमको आपने पूरा lecture दे दिया. But what are we going to see out there in the sky? हमारा telescope देखेगा क्या? So you see, we gave this prediction कि when you see, much higher frequencies from a region in the sky, maybe it's actually the, singularity or a fireball. A lot of very interesting astrophysics you see around the singularity, what are called, accretion disks around black holes and singularities. This is just, cartoon of an accretion disk around a singularity. It will create jets, you see, massive jets, which are seen from astrophysical sources out there, galaxies and so on. But really coming to the end of my talk, I'll tell you, you see this massive collision of black holes or singularities also. What will happen, when these monsters, gravitational monsters, you see, collide? हम देखते हैं ना आजकल तो बहुत रामायण और महाभारत वो सब चलता है. तो most of the time, you see the collisions of, विविध अस्त्र शस्त्र. एक साइड से एक अस्त्र आता है, दूसरे से, और फिर पता नहीं वो क्या annihilation होता है. But, that annihilation or that collision, scientists actually observed. I mean, I'm not talking of Ramayana, by the way. I'm talking of quantum gravity. You see, I'm very, very, हम वफादार है अपने जो टॉपिक है I'm very honest and, sticking to my subject. So I'm talking about quantum mechanics, or rather quantum gravity. These huge entities, collided out there in the skies. And then this LIGO, the massive 4 kilometers by 4 kilometers antenna, saw what are called the gravitational waves coming out from that collision. And then that is the signal. I mean, right now, the physicists are analyzing, are there any quantum gravity signatures in this kind of, collisions? The gravitational waves, are they coding any, signals from the, quantum theory playing the part there and the gravity playing part there? Another thing is the Event Horizon Telescope. We are observing the center of our own galaxy. So maybe a naked singularity or a black hole is sitting there. पूरा massive radio telescope create किया है. You see, Earth के different radio telescope को connect किया है. Global connectivity. So an Earth-size radio telescope has been created. And the bigger the telescope, the smaller you can see. So galaxy ka center, and they have tried to, this is the galactic center in this, picture in the square that you see. So that kind of effort is being made. The key point, let me now really summarize. The key point is general relativity implies the existence of very strong gravity regions where both quantum gravity and general relativity come into their own. And then, as Robert Wald, a very famous physicist, pointed out, if the singularities are seen, then in a literal sense, we would come face to face with the laws of quantum gravity. Whenever gravitational collapse to a naked singularity occurs in the distant regions of our universe. So I'm telling you this, research frontier. So what I'm really telling you is, are singularities some kind of a quantum gravity lab? Because ultimately, I was telling you earlier, the theories are not making much progress. We need to have observational signatures. And in order to get those observational signatures, it is very difficult to create those kind of laboratories on Earth. So nature has created, such laboratories out there on skies. You don't have to spend billions and billions of dollars. खैर अभी तो हमारे पास billions of dollars है भी नहीं. So सब crash, economical जो crash है, so science funding may be a worry. But then this, labs in the skies we can explore. A lot of this discussion is given in my Oxford University Press book, The Story of Collapsing Stars. This is the international edition, but I have convinced them to bring out, an inexpensive Indian edition also. You can see it, there. And the very last slide is that of our research paper in Physical Review, Letters, PRL, few years ago. By PRL in Gujarat, we understand Physical Research Laboratory. But scientists understand by PRL, the Physical Review Letters, a famous journal, actually. So in that paper, what we pointed out is that when you bring in the quantum gravity effects, a massive star collapsing will, in the very final stages of a collapse, radiate out in a very massive way. Okay? So there will be a burst-like radiation which would almost look like an explosion in the sky. we see this gamma ray bursts, almost one every day, radiating energy as much as the entire sun will radiate out in its entire lifetime. पूरा सन जो है अपना entire lifetime में जितना energy देगा, that much of energy will come out in a matter of few minutes. So that kind of a burst-like energy you can get if you put in quantum gravity effects into the final stage of a massive star. And you will see, a massive explosion, something like this. So I think with this, I end my talk. I have tried to give you, some kind of glimpses why the quantum mechanics or quantum theory is so very important in astrophysics, in cosmology, the wonderful, researches that have been made, the wonderful developments that have been done in quantum theory, in quantum mechanics. We take them in full, seriousness, and then we try to unite it. The problem is indeed very, very formidable. The best of the minds of the world at Princeton, Harvard, everywhere, Cambridge, they are trying to, do it. And the end is still not in sight, I would say. So, it is the inspiration to the listeners, the young students, the young, bright faculty who might be present here. And, let us all work together, go further. I warmly thank the MS University of Baroda, the Academy, Gujarat Science Academy. I did not thank, but I warmly thank still my colleagues. I can't stop thanking them. Without their enthusiasm, all this, and of Professor Arun Pratap, we thank all the colleagues and, of course, the technical team, Chintan and Harshal and all the good friends. Okay, thank you very much, listeners. Thank you again.
Sir, thank you very much for a very wonderful, interesting, informative, and inspiring talk, sir.
Thank you.
Really, we understood the role of quantum gravity and quantum gravitational nature, sir. And really, you nicely explained the frontiers of research to our young students. Sir, we sincerely thank you for a wonderful talk. And now, sir, we have a questions answer session. So I will request Jignesh Pandya to conduct the session. Over to Jignesh Bhai.
Yes, Jignesh. I see many questions on the screen also, but let Jignesh make it.
Yes, sir. Sir, he is handling this session. So
yes.
Jignesh Bhai, are you on the line?
If he is not there, I can read out.
Yes, sir. You please read that there is a questions in the chat box. You can select the questions and please answer.
Hello.
Yes, sir. Yes, sir.
Okay.
Jignesh, sir.
Yeah, I'm
yes,
here.
Sir. Yes, sir. Please proceed.
Okay. Sir, the first question is on the topic of grand unified theories, which one is the most preferred and has a potential to do better for quantum gravity? Is it loop quantum gravity or string theory?
Okay, wonderful. I have in a way, tried to answer this question in my early part of the talk. Really, each of them have severe limitations. And what I really tried to, drive home in my entire session is that we really need, observational signatures, observational markers, really. without observational markers, I do not think we can make really important or great progress in this particular, either be it, string theory or be it loop quantum gravity. I would say that both are struggling today. वो कहते हैं ना कि पानी में से सर ऊंचा रखने की ट्राई कर रहे हैं. So how to keep their head floating? You see, it is a pity. Most brilliant people have devoted, huge time, but both have, come out with severe limitations. We need really a different kind of, pathways. And that is what I really have tried to indicate in my lecture. Look for actual quantum gravity laboratories out there in the sky, and the space-time singularities will provide you that kind of a laboratory. This is what I have emphasized.
Okay, thank you, sir. Another question is by V. Ashokan. He is asking, yeah, he is asking, does time play a major role in black hole?
Oh yes, the time plays a very important role. There is a lot of discussion on, the flip of time signature near the event horizon. I must use a little technical language. The space-time metric, the Schwarzschild metric, which is typically taken outside a black hole, that, flips its signature. So as they say, the time becomes space and space becomes time, close to an event horizon. So, the time plays a very important role. But Jignesh, I see a very interesting question here by
Yes,
Vivek Pathak. If you don't mind, can I?
Yes, please, sir.
And then you come back. You see, Penrose gave, Vivek Pathak is asking, Penrose gave cosmic censorship hypothesis, which says that naked singularities are unphysical. So does naked singularity exist in nature? See, the hypothesis, Vivek, was given in 1969. That is more than 50 years ago. Now, hypothesis, as you know, you must prove it. No one could prove it. In the meantime, you see, as I was describing in my talk, I believe the recording is available on the Facebook or wherever. You see, the physicists over past decades have discovered many solutions to Einstein equations where the event horizon does not form. Yesterday, Professor Lokanathan was mentioning, you see, Professor Vishweshwara, or I think in his introduction, Madhusudan mentioned, Professor Vishweshwara was a great friend, by the way. You see, after I completed my PhD, he had invited me to Raman Research Institute to give a set of lectures. So, you see, Professor Ghatak also told us, you see, wonderful mysteries of quantum mechanics yesterday. What I was trying to tell you right now was that we have come up with, very physical solutions of Einstein equations, which give out, the solutions where singularity is visible. It is naked singularity. Now there are papers from Princeton, from Cambridge, from Harvard. You just look at, our list of papers on Inspire, this CERN high energy physics website. The citations are growing to this Indian works. So by now it is very widely accepted that this singularities, visible singularities are very much there. But you see, Penrose is a big name, and whatever a big name says, you see, goes on for a very long time. So in fact, we had a very, tumulus or, torturous. My friends used to tell me, oh, you are speaking against Penrose. Tumhara chutney ho jayega. You see, kachumbar, ya to kehte na khima. You see, what you should do, what Tata Institute friends used to say, you see, what you have to do is you have to visit Cambridge, you have to, visit Penrose, वहां जाके 2 महीना रह के वापस आने का, तुम्हारा कल्याण हो जाएगा. बस. You see, you have to be careful. You see, here also you have to be politically correct. You see, वो तो politically correct रहना है तो सीधा politics में ही जाते ना. अभी पैसा बनाना है तो industry में जाओ. इतना mind, इतना, see the kind of things you see. These eminent people were telling you yesterday, if they had applied to IT or computers, you see, they would have been not millionaires but billionaires.
Right.
So why they are doing all this, you see, even, in their, 7th decade or, even the Professor Lokanathan, even in there. So they are after, the unity of nature. That is their joy. वो billionaire बन के और Forbes list में उनको नहीं आना है. So here the point is now this is a progress, new paradigm change in science. You read out, you see, you will see many reports. Give my name, Pankaj Joshi and Naked Singularity in Google. You will find articles, you see, in Physics World and New Scientist and, Nature and, many. So there have been a lot of developments. So sorry, I took out of turn, Jignesh. Please.
Yeah, no problem, sir. I think, sir, there are more than 65 questions right now.
Yeah.
So we'll collect the questions and send it to you, sir.
Absolutely.
So, yeah, now I think because it won't be practically possible to go to all of them right now.
Yes.
So shall we close for this thing?
Yes, thank you. Thank you.
Yeah. Thank you very much, sir.
Thank you, sir.
Thank you.
तुषारભાઈ અનમ્યુટ કરવું પડશે તમારે.
Can you hear me?
Yeah.
Now.
Okay. Well, friends, we will start the second session. And
अनम्यूट करो तुषार भाई, अनम्यूट करो आप.
now can you hear me?
Yeah.
Okay. Well, friends, for the second session, our speaker is eminent speaker is Professor V.N. Potbhare, sir. Friends, he is another Amitabh Bachchan of our Gujarat Science Academy and an excellent orator. We are very fortunate that Professor B.S. Chakrabarty is with us right now. He is closely associated with Professor Potbhare, sir. Professor B.S. Chakrabarty is a head of Applied Physics Department on Faculty of Engineering and Technology of MS University. And friend, he is a director of IQSC cell and a pioneer researcher in the field of luminescence. With this brief introduction, I will request Professor B.S. Chakrabarty, sir, to introduce our eminent speaker, Professor V.N. Potbhare, sir. Over to B.S. Chakrabarty, sir, please.
Thank you, Tushar bhai.
Thank you, sir.
It's indeed a privilege and an honor to introduce Professor V.N. Potbhare. In fact, we had learned a lot as young teachers from him, and he was a kind of path bearer for us. So it is really a honor and privilege and to put forward his credentials, although I find myself too small to do the job. On a formal note, he has done his PhD from Rochester University, New York. He did it in 1975. And he has to his credit a postdoctoral fellowship at the University of Toronto. This was in 75-76. After which he joined as a research scientist at Physical Research Laboratory and remained there from 76 to 78. Thereafter, he joined as a faculty at the South Gujarat University, after which he had a stint at the Faculty of Science, the MS University of Baroda. And thereafter, he was, for the bulk of his time, he was at this department, the Department of Applied Physics, Faculty of Technology and Engineering, the MS University of Baroda. His area of research is theoretical statistical nuclear physics and random matrices. Well, that was on a very formal note. Of course, being so long with him, we have developed our personal bonds with him. And to be very honest, he has inspired us all, you know, for in a lot of ways. And I can easily say in all authenticity that he has left a very rich legacy of academics and research in the department. And his, I would say, his dedication to the cause of physics is exemplary. As a person also, I would like to mention one thing about him as a person, that this is particularly for the youngsters and the young teachers, that whenever I found him a little bit unhappy or disturbed, he used to take resort to physics books. He used to just go to his room and open his books and start reading. Now that is his dedication to the physics cause. Apart from that, he tried to motivate the students. He took a lot of classes to coach the students for NET, SLET and all these exams. He was a motivation to us youngsters also. And sir, on a personal note, Professor Potbhare, you had said, you had put forward a set of objectives as the head of the department for this department. And as the present head of the department, I now understand what was the importance of it. And your endeavor of cross-breeding in the department by acquiring a lot of talent from outside has borne its fruits. And let me inform you with all humility that this department has now taken wings in terms of the research and academics and gone quite far. And right now, in terms of research credentials, we are doing quite well. And our cumulative H index is right now at around 40 of the department. We have on an average around 50 publications per year. And over the last few years, we could get almost 4 to 5 crores of rupees as grants from various agencies. With this, sir, I welcome you and I look forward to your inspiring lecture. Thank you. Thank you, sir. Over to you, Potbhare, sir. Thank you.
Sir.
Hello, can you hear me?
Yes, sir. Yes, sir.
Okay. So I thank you all for joining this particular webinar. I thank you, Professor Arun Pratap, for inviting me at this particular place. The topic that I'm going to talk about is basically fundamental topic in quantum mechanics. It is the uncertainty principle. Let us begin the topic straight away. So as far as the science is concerned, this is just, there are many important events that occurred in science. I have listed them in order, not in any order, but just the way that they came to my mind. One of them is Origin of Species by Darwin. Then another important process is synthesis of urea in laboratory by Wöhler, which basically made that organic chemistry can be studied in laboratory. Understanding of genetic code by Crick and Watson. invention of number system and role of zero in real and complex plane, Fleming's discovery of penicillin. Another important theorem is Gödel's impossibility theorem, which is very important in our studies also, because yesterday somebody was talking about that can quantum mechanics tell everything about science. Well, Gödel says that whatever, because every science has certain assumptions, and Gödel has shown that it is impossible to derive everything or prove everything using these assumptions. So therefore, quantum mechanics cannot answer all the questions, because nobody can answer all the questions. In our Upanishads, there is a statement which basically says, Sahasraksha Sahasrapatha Sabhumim Vishwato Vrutvat Atyatishtat Dashangulam. He says that the God has thousands and thousands of eyes, thousands and thousands of hands, and so on, and it stays, it envelops the entire universe, but it stays 10 angles, 10 things about that particular thing. That means even God cannot be explained by using our assumptions. Anyway, that is another thing. As far as the physics is concerned, Newton's theory of gravitation, Oersted's experiment, Maxwell's equations, Einstein's theory of relativity, thermodynamics, quantum mechanics, nuclear energy, these are the basically the signposts in physics. Let us go to, and then the list is actually very long. Each of these basically has changed our thinking and has revolutionized the science. As far as the topics are concerned, everything in this world is connected to one another. All right. We actually compartmentalize because we call ourselves physicists, some chemists call chemists, and so on and so forth. There are different departments and so on. There are rivalries in the department. But as far as that is concerned, we compartmentalize simply because our time is limited, our brain size is limited. In principle, this compartmentalization is basically because of our inability to understand everything. There is a poem by John Donne which basically says, no man is an island entire of itself. Every man is a piece of the continent, a part of the main. Any man's death diminishes me because I am involved in mankind, and therefore never sent to know for whom the bell tolls. This is basically a mythological poem which basically for whom the bell tolls. The bell normally tolls in the Christian villages or Christian area where a certain person has died. And the John Donne is basically saying that it tolls for thee, because not only that person has died, because that person has a part in you. So therefore, everyone is connected to each other. So therefore, it tolls for thee. Anyway, let us come to the quantum revolution. Quantum revolution started beginning of the last century, and still it is not completely understood. Right. That is because quotation, as Professor Feynman has already, this particular quotation was yesterday mentioned by Professor Lokanathan and Professor Ghatak. There was a time when newspapers said that only 12 men understood the theory of relativity. I do not believe that there ever was such a time. On the other hand, I think, and I can safely say, nobody understands quantum mechanics. Nobody knows how it can be like that. This is a quotation from Character of Physical Law, which is written by Professor Feynman. Similar feelings Professor Einstein also mentioned. This also was mentioned yesterday, that all 50 years of my conscious brooding brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick and Harry thinks he knows it, but he is mistaken. That is basically what Professor Einstein wrote a letter to his friend. The main concept which gives the uncertainty principle, Heisenberg's uncertainty principle, is basically the question of duality. The duality is basically wave-particle duality. Light, as we know, shows interference effects, Young's double-slit experiment, then photoelectric effect, and matter has electrons, protons, and neutrons. So light as an interference basically shows a wave character. Photoelectric effect shows the particle characteristic, while matter, electrons, protons, and neutrons, particles, these are particles as Professor J.J. Thomson proved in earlier of the last century, and his son, basically another Thomson, showed that it is a wave. So therefore, description of a particle and description of light as a particle as well as wave, that basically corresponds to duality. This basically is a concept in our philosophy also. Our philosophy also talks about duality, Dvaita and Advaita. Anyway, let us not go into philosophy right now. Let us look at the uncertainty principle, which basically says that if it's a description as a wave, if matter is described as a wave, if light is described as a wave, then the wave basically is in infinite extent. It goes from minus infinity to plus infinity as far as one dimension is concerned. So therefore, in that particular case, its uncertainty in position is infinity, because it is present everywhere. As far as that part is concerned, the momentum uncertainty automatically is zero, because then the momentum is basically certain. If we describe that as a particle, then particle is at a particular place. And as far as if the particle is at a particular place, its uncertainty in position is zero. But whenever that particular wave function is described as a Fourier transform, it corresponds to have a waves which are superposed with waves from minus k is equal to minus infinity to plus infinity. So which basically means the momentum uncertainty is infinite. So therefore, as far as the product part is concerned, actually all particles, whenever we talk about electrons and protons in anywhere, that particular thing, electron is not really at from minus infinity to plus infinity. It is localized. So therefore, it has to form a localized wave packet. So localized wave packet, whenever it's described quantum mechanically, corresponds to a superposition of many waves, when AK corresponds to the amplitude of that particular wave. There is a very important theorem in Fourier transform mathematics, which basically says, it's written by Bracewell, and it says delta x into delta k is always greater than or equal to half. Now this is a theorem in Fourier transform mathematics, and that particular theorem basically says that whenever a particle is described as a wave packet or a system is described as a wave packet, then in that particular case, delta x into delta px would always be greater than equal to h bar by 2. So delta x, of course, uncertainty in position is defined as the square root of average value of x square minus the average value of x whole square. Similarly, corresponding uncertainty in momentum is defined. Now, in this particular case, whenever we talk about uncertainty, the probability enters the physics. Probability enters the physics in two different ways. One different way, it occurs in statistical mechanics. It occurs in statistical mechanics because there are so many number of particles that are there, and therefore it is our inability to know the position and velocities of all the particles, and therefore we are unable to do the calculation, and therefore that basically corresponds to this is due to our inability to do the calculation and keep the track of all the particles. The second kind of probability enters quantum mechanics, as the quantum mechanics wave function is written down as psi, or the probability of finding a system at a particular place is psi star psi. That is the interpretation given by Born, and that quantum mechanics basically is due to its intrinsic character. Anyway, the quantum mechanics also, we have entrance of non-locality. All laws of physics earlier are considered to be local. That force on a particle is local and acceleration of a particle is local. So all these things are local. Whenever the quantum mechanics comes in, it automatically brings in the non-locality. That means the effect can be seen at somewhere else. We will come to that later whenever we talk about uncertainty principle. Now, as far as the uncertainty principle derivation is concerned, I am not going to talk about the derivation of uncertainty principle because it is given in many textbooks. So let us go ahead. And what I will here before discussing anything, I would like to show you a quotation from Professor Feynman, whatever he wrote in his lectures in physics. He says the uncertainty principle protects quantum mechanics. Uncertainty principle protects quantum mechanics. Heisenberg recognized that if it were possible to measure momentum and the position simultaneously with a greater accuracy, the quantum mechanics would collapse. So he proposed that it must be impossible. Then people sat down and tried to figure out ways of doing it, and nobody could figure out a way to measure the position and momentum of anything, a screen, an electron, a billiard ball, anything with any greater accuracy. Quantum mechanics maintains its perilous but still correct existence. The reason why Professor Einstein always attacked uncertainty principle is because uncertainty principle is protecting quantum mechanics. And Professor Einstein wanted that the God does not play dice. He does not want probability in the world. And therefore, that particular, he was always attacking uncertainty principle. Anyway, what I am going to talk about are various topics that are there, which basically are given here as a list. And I don't know how far we can go as far as that particular list is concerned, but let us go ahead. So first of all, it is the gamma ray microscope, which basically brings us how the uncertainty principle comes into physics, because wavelength of light, whenever we observe anything, or let us say look at the microscopes observes any small quantity, small object, then in that case we are using light as the source of information, so whenever the light is used, the limit of resolution is of course lambda by 2. So delta x, now of course that basically means the whatever is the objective of the microscope, that half angle of the objective is theta, and delta x, uncertainty in position, maximum uncertainty in position corresponds to lambda upon 2 sine theta, where theta is the half angle of the aperture of the microscope. So electron is certainly smaller than the visible photon, so we must use very small wavelength. So the small wavelength based so instead of using ordinary light, we use now gamma ray photon. Now the gamma ray photon has a momentum corresponding to P. Now if X-ray photon, gamma ray photon or X-ray photon enters the microscope in this direction or in that direction, then it has different theta that it enters. So therefore, X-ray X component of the photon, after scattering anywhere in that particular in the lens of the microscope, uncertainty corresponds to P sine theta. So the X component of the momentum corresponds to P sine theta. So the momentum of course is conserved. So delta x, delta px corresponds to greater than h by 2. So this is how the basically whenever we want to observe anything, we cannot observe the quantity. If there is uncertainty in momentum, there is corresponding uncertainty in the position and corresponding uncertainty in the momentum. Similarly, diffraction experiment was yesterday talked about, and that also shows that there is uncertainty in the position as well as uncertainty in the momentum. Let us go ahead. One of the important milestone is an experiment that proposed by Einstein. There is a story that always goes on, and in fact it is written down many places, that whenever the Solvay conferences were there in Europe, Einstein would be present, Bohr would be present. The story goes that in the morning, Einstein would talk about how the uncertainty principle can be violated or it is not valid in a certain region, and then he would talk to this to Bohr, Heisenberg and others that are there. Heisenberg and others would never listen to that particular part, but Bohr seriously took that particular thing. And by the evening, the dinner time, Bohr would have given the answer to the Einstein that your proposed experiment is not violating uncertainty principle, but in fact it is showing that uncertainty principle is valid. This is a famous experiment that Einstein proposed, that let us have a box which contains certain number of photons, and there is a shutter to that particular box that is controlled by a clock. So whenever that particular thing is then in that particular case, the mass of that particular entire box can be measured very accurately, and energy and mass are related to each other. So therefore, whenever the clockwork opens the shutter is open, the photon goes away in particular direction. So the mass of that particular box is reduced. So the mass can be measured leisurely, and the photon goes away. So the energy of the photon, so therefore the mass can be measured very accurately, and the energy also, energy can be measured very accurately, and the time also can be measured very accurately. So therefore Einstein proposed to Bohr that this particular experiment shows that delta E delta T is not valid. Now there is a argument that Bohr gave. Bohr at that particular time used, in the evening, told Einstein that, Professor Einstein, you forgot your own theory. You forgot your own theory of general theory of relativity, because general theory of relativity says that whenever the gravitational potential changes, there is a change of rate of clock, and if that particular thing is taken into account, then you will immediately realize that delta T delta E is always greater than h bar. Anyway, that is the main important experiment, or the crux of quantum mechanics is in double slit experiment. Double slit experiment basically is, here is an this is a figure from Feynman's lectures in physics. This says electron gun has two slits, and then there is a detector. If one slit is open, you obtain, this was also discussed yesterday by Professor Lokanathan and Professor Ghatak, and then one obtains, whenever both slits are open, we obtain an interference pattern. So therefore, Tonomura, who is also mentioned yesterday, that instead of having many number of electrons flowing, if the number of electrons in the entire experimental system is always one at one particular time, then also one obtains this kind of interference patterns. So somebody asked that particular time, does an electron interferes with itself? Well, Dirac actually says that each photon or an electron interferes with itself, because a electron that comes at this particular time and electron that comes later time are not coherent. But each electron, when it passes through both the slits, now it passes through both the slits is a question. How does it pass through both the slits? Well, there is a probability of passing through this slit, and there is a probability of passing through this particular slit. And if that is taken into account, then in that particular case, we obtain an interference pattern. So the interference pattern is an example of electron behaving like a wave. And of course, the question is, whenever electron is detected, it is detected as a particle. But whenever it moves from one place to another place, it moves like a wave. So therefore, both things are together. Yesterday, people were asking whether electron is a wave or electron is a particle. And then Professor Feynman used to say that neither electron is not a particle, electron is not a wave. In fact, he gave a name to that particular thing. It's a wavicle. Wavicle basically means it's a combination of wave and particle. Now that particular experiment, electron experiment, has now can be conducted, and this is an example. This is an example where the carbon-60 buckyball, all right, such a large system also shows interference pattern. Now this is an experiment that has actually been conducted, and this is the same kind of an experiment with buckyball with lower resolution. But this is a resolution that is, this is an interference pattern on molecular interference, which basically says phthalocyanin. It's a complex organic molecule, and such a large molecule also it's showing interference pattern. So the interference pattern is not only shown by photons, electrons, it's actually shown by many large molecules also. All right. Anyway, let me go ahead and actually look at the applications of quantum uncertainty principle. Now, it is a funny question, funny way to say that applications of uncertainty principle, because uncertainty principle is not an equality, it is an inequality. So whenever it is an inequality, we cannot actually derive things exactly, but we can understand many things using that uncertainty principle. And that these are basically what are the that gives us physical understanding of many phenomena in nature. First of all, it was used to show that electrons cannot remain inside the nucleus, because whenever the matter was studied, first of all, the protons were known and electrons were known. Electrons were the first thing that were discovered, and protons are the part. So the nucleus, when Rutherford discovered that particular size of the nucleus, then in that particular case, the initial model was that the nucleus is made up of protons and electrons, because helium-4 basically has 4 protons and 2 electrons inside. That was the idea that was used earlier whenever the neutron was not discovered. But anyway, electrons, then later on one really found that electrons cannot remain inside the nucleus. Electrons do come out of a nucleus because of beta decay, but these beta decay electrons are not there, already there inside that particular nucleus. They are actually generated at that particular time. And this can be shown because the radius of the nucleus is of the order of 10 to the power minus 13 centimeter. So therefore, delta P, it corresponds to roughly h upon R0, and which corresponds to a value which has a relativistic formula has to be used, and that basically gives the value of about 200 MeV. So if electron is inside the nucleus, it must have kinetic energy of the order of 200 MeV. Now, the question may occur, delta P is of that particular order, why the momentum should be of that order? Now, if you look at the equation of delta P basically says expectation value of P square minus the square of the expectation value of P square root. Now, expectation value of P is 0 because the electrons inside the nucleus. So the expectation value of P must be 0. So the expectation value of P square, which corresponds to uncertainty, and that basically corresponds to 200 MeV. Now, if the electron comes out of the nucleus, it must have kinetic energy of that particular order, of the order of 200 MeV. But as far as the beta decay is concerned, beta decays, the electrons coming out of the nucleus do not have energy much larger than few MeVs. Even if I consider that the electrons are attracted by the positive nucleus, and that particular energy, even if for the uranium, if I consider Z is equal to 92, that potential energy would be roughly 125 MeV. So therefore, if the electron has kinetic energy 200 MeV, it has to spend 125 MeV to come out of the nucleus. Then in that case, it should have 75 MeV. But no such beta decay with such large energy exists. So therefore, it turns out that electrons do not exist inside the nucleus. Well, do protons exist inside the nucleus? Do neutrons exist inside the nucleus? The momentum basically is the same as the electrons, since uncertainty is the same as the radius of the nucleus. But the mass, however, is 2,000 times larger than that mass of the electron. So therefore, we use non-relativistic treatment, and then the kinetic energy of the proton and the neutron that is necessary for the proton to stay inside the nucleus or neutron to stay inside the nucleus is of the order of 20 MeV. And then one knows very well that the potential well, that is Woods action potential well that is used for the nuclear physics is much deeper than 20 MeV. So neutrons and protons can remain inside the nucleus. So that is one important thing, that the first application, as the neutrons can exist inside the nucleus, protons can exist inside the nucleus, but electrons do not exist inside the nucleus. Then another important thing that is basically explained qualitatively by the uncertainty principle is stability of matter and the origin of repulsive interaction. Now, there are two requirements for stability. One requirement is that it must have an attraction at long range and it must have a repulsion at short range. Both things are necessary for stability to occur. So for hydrogen atom, there is attraction due to Coulomb interaction, which corresponds to 1 over R force, potential energy as 1 over R, while the kinetic energy, which corresponds to H upon delta P, because H upon delta X, H upon R. So the kinetic energy is of the order of 1 over R square. So therefore, if the electron is attracted towards the nucleus. As it comes nearer, its potential energy falls, but its kinetic energy increases as 1 over r square. And therefore, it cannot increase that tremendously. And therefore, electron cannot fall inside the nucleus. And that is basically what comes because of the uncertainty principle. So the repulsion is because of the electron coming closer to the nucleus. And that repulsion is due to uncertainty principle. Same thing can be explained for the ionic bond of sodium chloride. Sodium chloride, as we know, standard basically says that sodium is positively, the sodium gives out an electron and chlorine accepts an electron. Then sodium ion, chlorine ion, both are spherically symmetric. Since both are spherically symmetric, they will attract because of the Coulomb interaction. But of course, they never fall into each other, because whenever they come closer to each other, electron orbits start coming closer and closer, and electron distribution becomes denser and denser. That basically means uncertainty in the position of the electrons goes on reducing, which means that uncertainty in the momentum goes on increasing, which means the kinetic energy goes on increasing and total energy goes on increasing. And therefore, reduction in position in uncertainty increases momentum. So that requires increase in energy, and therefore we realize that there is a repulsive interaction. So without that repulsive interaction, we cannot exist, because without repulsive interaction, nothing can be stable. Now, we know that Professor Bohr in 1913 gave the picture of hydrogen atom as an orbit. Now, the way Professor Bohr derived that particular relation is quite unique. Of course, that is not I'm going to talk about. So that is another aspect, that Professor Bohr actually derived that particular relationship not by quantizing angular momentum. He derived in a different way. And quantization of angular momentum is a result of that particular derivation. Anyway, we assume that quantization rule is given as momentum multiplied by r is n times h bar. Now, however we want to talk about the orbit of a particle, orbit of an electron, then in that particular case, we have to talk about, whenever we talk about an orbit, the delta r, that uncertainty in the position or the uncertainty in the radius must be much smaller than r. Then only we can talk about an orbit. We can talk about, and similarly, in order to talk about the velocity of that particular thing, delta p must be much smaller than p. So therefore, if I consider both things together, delta r by r and delta p by p must be much smaller than 1 if I want to talk about an orbit of an electron. Now, uncertainty relationship says that delta r, delta p must be greater than or equal to h bar, approximately h bar by 2, but let us consider h bar. In quantum mechanics, as far as the uncertainty principle is concerned, h and h bar by 2 are more or less similar. So therefore, delta r, delta p divided by rp, which basically must be much smaller than 1. But delta r, delta p is greater than h upon r upon p, and r into p corresponds to n h bar. So therefore, this particular quantity must be is equal to 1 over n. Now, if a, that is this relationship, and this relationship has to be valid, then in that particular case, n must be much larger than 1. That means we cannot talk about the ground state orbit or the first orbit or the second orbit or the third orbit. In order to talk about an orbit, then in that n must be very large. Now this relationship, so therefore this is concept we saw as far as the ordinary n is equal to 1, n is equal to 2 is concerned, we cannot really see an orbit as such. But anyway, this is famous celebrated correspondence principle by Bohr, that whenever the quantum numbers are very large, then the electron or that particular system follows the classical rule, and that is correspondence principle, and that was used by Bohr in order to obtain the his model. The Bohr's model is merely a way to obtain correct energy spectrum of the hydrogen atom. Anyway, now let us come to a peculiar situation that occurs. All right, that because this is a benzene molecule. Benzene molecule corresponds to C6H6. Now, normally that can be written down as 3 double bonds and 3 single bonds. Now, it is known that Kekulé is the person who actually gave that particular structure of gave the structure of the benzene. And there is a story about that particular thing, that he dreamed about that particular thing, that he was very worried about what kind of bonds that are there in benzene molecule. So therefore he slept in his chair, and then he dreamt that a snake is eating its own tail. And that from that he realized that the benzene molecule is a cyclic molecule like that, which is a double bond. And so therefore there are two structures, structure 1 and structure 2. The double bonds so therefore there is no distinction between carbon-carbon bonds in benzene. So the double bonds and single bonds must exchange each other. Now chemists are very clever people, and they have actually realized that the single bond length is of the order of 1.54 angstrom, and the double bond length is of the order of 1.34 angstrom. This is studied from various molecules that are there and studied by chemists, and they actually come up with this particular data. But if you look at the benzene as such, the bond length in benzene is neither 1.54 nor 1.34, it is 1.40 angstrom. So therefore it's between single bond and the double bond. So therefore it basically means the double bond and single bond are vibrating, or they are exchanging with each other. And that basically corresponds to that the double bond basically corresponds to pi electrons. And these pi electrons are going from one place to another place. So the electron localization is not there. It's delocalized. So delocalized means uncertainty in position of the electron is larger, which basically reduces the uncertainty in momentum, and that reduces the kinetic energy. Actual work, if you realize that as a consequence of electron delocalization, there is extra binding energy. This is called resonance energy, and that resonance energy is 37 kilocalorie per mole, which when we convert to actual 1 per molecule, it is 1.6 electron volt per molecule. Now 1.6 electron volt per molecule is quite a large number, because whenever we burn anything, the carbon is burnt, one carbon is burnt to carbon dioxide, roughly the energy released is of the order of 5 to 6 electron volt. So therefore, whenever benzene molecule, extra energy is 1.6 electron volt per molecule. And similarly, whenever we talk about naphthalene molecule, naphthalene is a double ring. So here is a single ring. Naphthalene molecule is a double ring. Double ring molecule basically says that it has roughly the 75 kilocalorie per mole, which is roughly double the binding energy here. So now let us go ahead. So this is another place where that resonance structure or uncertainty principle plays a very important role. It plays a very important role in formation of proteins. Proteins are formed by the bond called peptide bond. The peptide bond corresponds to COONH. That is what the peptide bond corresponds to. Now, actually peptide bond, now here the double bond between oxygen and carbon gets shifted to single bond, and that basically electron, the double bond and single bond goes on fluctuating. So that is called basically resonance. So this peptide bond basically gives extra binding energy, because the delocalization of electron, it produces less amount of uncertainty in momentum, meaning less in kinetic energy, and that energy is roughly order of 23 kilocalorie per mole. That is 1 electron volt approximately. So therefore, the peptide bond is much stronger than a single bond or a double bond, simply because it has extra resonance energy, and this extra resonance energy gives strength to protein molecule. Not only that, if this was the structure of the peptide bond, then the peptide bond would rotate around that particular single bond. The molecule would rotate, one amino acid will rotate against another amino acid. But since that has a partially double bond character, the amino acids do not rotate with each other, and that gives the structure to the protein molecule. So therefore, that has important effect on the shapes of protein molecules. And that is basically data which says that carbon's N double bond length is 1.48, carbon nitrogen double bond is 1.28, while actual length is 1.32. So it basically forms a resonance between, so electron goes from one place to another place, delocalizes, which increases the binding energy. This is another example which I taken from the book of Feynman, which says the positively charged hydrogen molecule ion. An electron is, whenever we talked about hydrogen molecule ion, that means two hydrogen atoms, one electron has gone out. So therefore, there is only one electron between two protons. So if there are only one electron between two protons, the electron can be associated with one proton, or electron can be associated with another proton. So if they are too far away, then one is hydrogen atom, another is a proton. So therefore, these are, as far as the quantum mechanics is concerned, these are two basis states. One basis state corresponds to electron near one proton, and second basis state corresponds to electron within near the second proton. But as we know, in quantum mechanics, the superposition of states are very important. That if the two states are possible, a superposed state is also possible. So therefore, you can immediately see that as far as the basis state is concerned, you can always make a state called number 1, and that corresponds to 1 minus 2, and 2 which corresponds to 1 plus 2. So these are the two states that are there, which are obtained by the superposition. And it turns out that if I have a state capital I, capital 1, that is state number 1, and state number 2, now you realize that state number 2 has this has plus sign in between. Plus sign in between basically means electron can be found at the center of that particular thing. So electron that in that particular case is delocalized more, while in this case the localization is more, and therefore state number 1 and state number 2 must have larger binding energy. That means it must be lower in energy. And that is so compared to state 2, state 1 has more spread out electron wave function, and delta x is larger, delta px is lower, hence lower in energy. So that basically means uncertainty principle qualitatively explains why state 1 is lower in energy compared to state 2. That is because the electron is inside at the center of the nucleus, center of the two protons. The probability of finding electron there is there. In principle, of course, one can solve the entire thing. You can write down two-state matrix. Electron jumps from one proton to another proton. Detailed analysis one can see in the book of Feynman. This is basically what is the graph that basically corresponds to. State 1 has this kind of energy as it goes up, while state 2 has a minimum, and therefore that is a bound state. So therefore hydrogen molecular ion is bound simply because of the uncertainty principle. Same thing can be talked about for the hydrogen molecule. Now I'm not going to talk about this particular part simply because if one wants to study this is given very nicely in Feynman's lectures in physics volume 3. Now let us come to another phenomena which comes because of the uncertainty principle, and that is the natural line width. Natural line width basically comes because of the uncertainty principle. Delta E, delta T greater than h bar by 2 relates the lifetime of an excited state with the uncertainty of its energy. Whenever a electron, let us consider an example of hydrogen atom. Whenever hydrogen atom is in excited state, so electron is in higher state, and then it comes to lower state. It makes a transition. So whenever it makes a transition, the transition time basically is controlled by quantum mechanics, right? So quantum mechanics is probabilistic. So therefore, the time for a transition is not fixed. So there is uncertainty in time. That uncertainty in time basically produces that particular energy is also uncertain. So the photon that comes out because of the transition from one state to another state has an uncertainty in energy, and that uncertainty in energy basically gives rise to whatever is the band, the width of a natural of a line. If you look at any line in a spectroscope, the line in spectroscope is never a single line. It is a Lorentzian profile, and that Lorentzian profile is produced because of the uncertainty principle. That time for transition is not certain, time for transition is not known, there is uncertainty in time. This is basically, that gives the line width of any line. This is, if we consider now, let us give an example. Let us take laser coherence time. Laser coherence time for ordinary gas laser is 10 to the power minus 3 seconds approximately. If I consider solid state laser, then it has a time limitation or coherence time of the order of 10 to the power minus 6 seconds. That means for 10 to the power minus 6 seconds, the light beam is entirely coherent. All right. And for ordinary light source, the tau, that time, is of the order of 10 to the power minus 12 seconds. So if I consider delta E corresponds to H upon H, delta E is H upon H into delta nu corresponds to H upon delta T. If I do the calculation, then it turns out that lower limit for solid state laser, if I consider 10 to the power minus 6 seconds, then the delta nu, that is the frequency uncertainty, is of the order of 2 into 10 to the power 5 hertz, while the ordinary light frequency is 6 into 10 to the power 17 hertz. All right, that is the ordinary frequency. So therefore, you can immediately see delta nu by nu is of the order of 10 to the power minus 12, which is very sharp monochromaticity. So therefore, whenever you say it is monochromatic, it is basically because delta nu by nu is coherence time is extremely large, 10 to the power minus 6, while for ordinary light, the coherence time is 10 to the power minus 12 seconds. Now, another important application, theoretical, I mean understanding kind of understanding of certain part of physics is basically that whenever we consider helium, helium is not liquefied, right? Helium cannot be liquefied. So no liquefaction of helium, right? Helium basically, whenever helium comes out, so therefore you immediately realize helium as a nucleus, helium has only interaction which corresponds to van der Waals interaction. So whenever helium atoms are separated, right, there's, so actually I should not say liquefaction of, actually no solidification of helium. It is not liquefaction, it is solidification of helium. So helium cannot be solidified. Potential energy is given as this, but this is basically potential energy given for the case of helium, that is from because of the van der Waals interaction, and this was calculated in 931. So VR has that particular part. So therefore, energy can be converted to temperature, and the K times T corresponds to energy. So therefore, the minimum of the potential energy of the order of 9K, 9 degrees. We cannot say 9 degrees, but 9 Kelvin, right? So for well-defined location in solid, so here the idea is not no liquefaction, it is no solidification. That is a mistake that is there in that particular writing. So this helium cannot be solidified, because if I want to make a solid, then in that case the position of helium atom should be of the delta X should be smaller than the distance between the two or the lattice distance between the two parts, and that is roughly of the order of half an angstrom. So if delta X is of the order of half an angstrom, the uncertainty in energy corresponds to the H or uncertainty in energy is H upon delta T, and H upon delta X is the uncertainty in momentum. And if I use that, the energy delta E corresponds to roughly of the order of 10K. So therefore, one realizes that the binding energy maximum can be 9K, while the uncertainty in the energy is 10K. So that basically means helium atom can never stay here in that particular potential well. It will always be above that particular part. So therefore, it is realized that the helium can never be solidified simply because of uncertainty principle. Now, the people actually ask the same question, that how can hydrogen be solidified? Hydrogen has a smaller mass. Hydrogen H2 molecule has a smaller mass than the helium, and therefore delta P, H upon delta P. So delta P. So if I consider that particular part, hydrogen also should not solidify, but hydrogen solidifies under large pressure. Hydrogen solidifies simply because hydrogen does not only have the van der Waals force, it also has force because of the interaction between the two hydrogen atoms, and that is basically even though helium does not solidify, hydrogen does solidify. Other noble elements do form solids because mass is much larger than that, and that is why helium does not solidify. Other noble gases solidify, hydrogen also solidifies. Now, this is another example where one can estimate the lowest energy possible for this. This is given mostly in many textbooks that basically says, let us estimate the ground state energy of the hydrogen atom. The ground state of the energy of the hydrogen atom corresponds to E square, potential energy E square upon R0, where R0 is the extent of spherically symmetric system. So the kinetic energy is of the order of delta P square by 2m is h square upon 2m r square. So the total energy is kinetic energy plus the potential energy, and that energy is total energy of the system. So if I want to find out the minimum energy of that, I differentiate dE upon with respect to R0, and that produces me R0, which corresponds to h square upon me square, which is basically Bohr radius. And the energy, if I substitute that in the energy expression, then in that particular thing, it gives me m e raised to 4 divided by 2 h bar square. So that basically tells me this is the actual exact energy of the hydrogen atom. It turns out that exact energy relation is an accidental perfect agreement. It is not that uncertainty principle gives you exact ground state energy of hydrogen atom. The accuracy, so it is basically accidental perfect agreement. It is not that uncertainty principle always gives that kind of an agreement. Similarly, for harmonic oscillator x0 is, as far as the harmonic oscillator is concerned, ordinary harmonic oscillator would say that the position of the oscillator or the particle should go at x is equal to 0. But if x goes to 0, its uncertainty in position is 0. Now uncertainty in position cannot be 0, because if uncertainty in position is 0, uncertainty in momentum is infinity, and therefore it would have infinite kinetic energy. So therefore one must realize that whenever we talk about harmonic oscillator in quantum mechanics, the x0 is roughly the estimated uncertainty of its position. So the particle is not at x is equal to 0, but it goes on vibrating around x is equal to 0. It goes on fluctuating around x is equal to 0. And if that is x0, then the total energy corresponds to kinetic energy plus the potential energy, which corresponds to half m omega square x0 square. And if I minimize that with respect to x0, the ground state energy turns out to be h omega by 2. So this is also another example how uncertainty principle explains certain things about ordinary things, that ground state energy of hydrogen atom and ground state energy of harmonic oscillator. Now let us come to another application of harmonic uncertainty principle. In statistical mechanics, we talked about statistical mechanics. There is probability that comes into picture. Statistical mechanics, one talks about the entropy of the system. Entropy of the system, as given by Boltzmann, is k logarithm of number of states, and the number of states corresponds to the phase space volume. Now, as far as the classical statistical mechanics concerned, that phase space volume can be utilized, and there is no need to have any unit cell for the phase space. But in quantum mechanics, that quantum statistical mechanics, Planck's constant h comes in, and that is the value of h. That so the phase space, elementary phase space volume, comes because of uncertainty principle is h cube if I have one particle, and h raised to 3n if there are n number of particles. Now this is another important thing that comes into picture. Now this recently I wrote a small article based on this particular thing, that is vacuum polarization and its role in spontaneous emission of radiation. Now emission of radiation is become important because of the laser. Laser, whenever we talk about laser, there are two kinds of emissions that are there. One is spontaneous emission and another is stimulated emission. Now stimulated emission, as we know, is occurring because there is already present the number of photons of that particular frequency. And Planck's law basically gives the black body radiation law, which was discussed yesterday, is given by that particular expression. And Einstein, by the way, this was given by Planck, and this was the Planck, and Einstein later on in around 1916 talked about this particular theory, which called Einstein coefficients are involved. So whenever two states go from one state to another state, there are two possibilities. R and M. N and M are the two states where N and M, one of them is lower energy state, another is higher energy state. Now naturally, M is stimulated emission is proportional to number of systems in the excited state. M is the excited state. So the stimulated emission corresponds to basically Bmn and I omega, that basically corresponds to the stimulated emission. And then Einstein wrote down spontaneous emission rate as AMM NM. Now this is the emission absorption rate naturally will depend upon how many number of photons are present, and that is what is the absorption rate is concerned. In thermodynamics, the Rmn and Rnm at thermodynamics, whenever equilibrium is reached, these two are going to be equal, and that basically gives that particular relationship. And Nm upon Nn corresponds to e to the power h omega by kt, that is Boltzmann distribution. And that is whenever Einstein used that particular relation, he obtained this relationship that I omega corresponds to AMN. And then when he compared that with the Planck's radiation law, he realized that A by B, BMM and BMN must be equal, and A by B must be equal to, and these are basically, this is where Einstein stopped. That is how far Einstein could go. Now, if you realize that as far as the ordinary light coming from the sun is concerned, then in that case, the sun has a temperature roughly of the order of 6,000 Kelvin, and the lambda corresponds to 4,000. Let us consider lambda as 4,000 angstrom. Then, as far as the light coming out, the ratio of spontaneous to stimulated emission is roughly of the order of 400. That means spontaneous emission is dominating. Similarly, lambda for 7,000, the ratio corresponds to 30. So there also spontaneous emission is dominating. So the domination of spontaneous emission is simply because of that particular large temperature. Now, as far as the laser radiation is concerned, we want domination of the stimulated emission, and that is basically what corresponds to. Now, if you consider that the emission rate contains that particular thing, if we consider the entire theory, that Rnm corresponds to D. Now, N omega is the number of photons that are present. Now, this basically is the rate that comes out because of the stimulated emission. But this one that is there, that is basically spontaneous emission. That spontaneous emission, one can consider that the emission of spontaneous radiation occurs because of uncertainty principle. Because of uncertainty principle, the photons, there are energy of half h bar omega that is present inside the harmonic oscillator or the mode of that particular vibration. And that half h omega basically produces vibration of that particular thing. So what is called 0-point fluctuation. And this 0-point fluctuation gives that particular thing. And 0-point fluctuation gives that particular factor of 1. And that basically means that spontaneous emission is also not necessarily spontaneous. It is because it is stimulated by the random fluctuations that are there inside that particular system. So random fluctuation is occurring because of the uncertainty principle. So it is the uncertainty principle basically talks about, gives us why there is stimulated spontaneous emission of radiation. Now one can also talk about that, whether now there are other spontaneous phenomena in nature. Other spontaneous phenomena in nature are radioactivity. That is alpha radioactivity, of course, one understands, because alpha particle is produced inside the nucleus, or is the 4 particles come together inside the nucleus. They are vibrating and they basically collide with the wall, and there is tunneling of that particular thing. That tunneling produces alpha radioactivity. But beta radioactivity, we talked about earlier that electrons don't exist inside the nucleus. So beta radioactivity means electrons are produced inside the nucleus. When the electrons are produced, these are also produced because of the quantum fluctuation of that particular field. So anyway, let us go ahead. And so here I talk about tunneling, barrier penetration. Barrier penetration is very important topic in our quantum physics, which this is from a book by I guess I forgot to mention the name of the book that is used. So therefore, this is basically whenever we consider that a particular system at energy E, then it will stop at that particular position. But there is uncertainty in delta x. So that delta x has a particular value. Similarly, delta x around that particular thing is this value. If these two delta x overlap with each other, then in that particular case, there is going to be penetration. So therefore, that penetration basically occurs because of uncertainty principle. Similarly, if you consider that penetration in terms of delta E, delta T, there is no fixed energy. So the energy goes up and down, and therefore the particle can come out of that particular thing. So this is another way of understanding why barrier penetration takes place. All right, of course, that. So if the wave function happens to be of the smallest uncertainty product, what is the smallest uncertainty product? Smallest uncertainty product is the product which basically produced by a Gaussian. And ground state of simple harmonic oscillator has a wave function that is merely just for the comment sake that Gaussian wave function is the ground state wave function of harmonic oscillator. Now, another important thing that occurs is the range of nuclear interaction. This is what Yukawa used in order to predict the force, that Yukawa force that is there inside the nucleus. The nucleus basically has size of R0, and therefore H upon R0 roughly of the order of MC. Now it is idea that all interactions are because of exchange of something. Electromagnetic interaction is because of the exchange of photons. Similarly, it is considered that the gravitational interaction is because of the exchange of gravitons. Similarly, one can consider that as far as the nuclear interaction is concerned, nuclear interaction is because of some kind of a particle that Yukawa basically assumed, and Yukawa predicted that the mass of that particle should be of the order of 2 upon 50 mass of electron. That is because if we consider delta P as H upon R0, then the mass that produces MC, which corresponds to for relativistic particle, and mass turns out to be of this particular thing, which is roughly 250 mass of electron. And then we realize that pi meson roughly has the same kind of mass. So therefore, Yukawa basically predicted the nuclear range of nuclear interaction. He said that if the pi mesons are exchanged between the protons and neutrons, and protons and protons and neutrons, then in that particular case, the range of nuclear interaction roughly of the size of the nucleus. Similarly, if we consider beta decay, as far as the beta decay is concerned, beta decay or weak interaction. Weak interaction is because of exchange. Now, beta decay is considered to be a small, very short range interaction. In fact, Fermi's theory of beta decay says that the nuclear beta decay interaction is zero range interaction. Zero range, of course, there is nothing like zero range interaction. So it must be very small range. So if the range is very small, the mass of that corresponding particle must be very large. And we know very well that as far as the weak interaction is concerned, two bosons are there, W bosons and Z bosons. They have roughly large mass, which corresponds to roughly 81 GeV and 93 GeV. So that basically is because of the new beta decay has a very short range. Now, this is another thing that one is, of course, one cannot really talk about that too much. It is basically whenever we consider superconductivity. In superconductivity, there is a coherence length. Coherence length in superconductivity. Now, as far as the Fermi energy is concerned, Fermi energy is EF, and that corresponds to m upon 2 Vf square. So therefore, delta E corresponds to Vf upon delta P. And if we consider that the band gap or the gap between whenever the Cooper pair is formed, the gap corresponds to roughly of the K times transition temperature. And if we consider that particular thing, then you realize that delta X, that is the Cooper pair, can extend to how long Cooper pair can extend, and that can be obtained, and that basically corresponds to this. So the Cooper length, if I substitute all the values for a relevant superconductor, then in that case, the coherence length roughly of the order of 10 to the power minus 4 centimeter. That is roughly the penetration depth of the superconductivity. The superconducting current flows through the surface of the superconductor, roughly thickness of that particular order. Now here I come to a peculiar situation, that is why that uncertainty principle does not seem to apply for a large particle, large system. I consider dust particle of 1 micron size, and then if I consider the mass of 10 to the power 1 micron size, you can calculate what is the mass, because the density of dust particle is roughly the density of silicon dioxide, 2.8. You can calculate the mass roughly of 10 to the power minus 15 kg. If the dust particle is in air, it vibrates. It is basically moving approximately 1 millimeter per second. And if you consider that particular thing, then in that particular case, you consider delta P by delta P. The wavelength of that particular particle is 10 to the power minus 6 angstrom, which is much, much smaller. So therefore, we consider that as classical particle, because wavelength, the de Broglie wavelength is very small. Now, as a novel exercise, I did that calculation for coronavirus diameter. Coronavirus particle. Coronavirus, basically, roughly, if you study that, it has roughly the size of 120 nanometer diameter. Now, coronavirus, of course, has two parts. One part is the protein structure that is outside, and inside there is an RNA that is there. So the mass of coronavirus can be calculated, assuming that the density of coronavirus, density of all living matter, is roughly 1 gram per cubic centimeter. That is density of our density of water. And if I consider that, then in that particular case, the mass of that coronavirus particle comes out to be 10 to the power minus 15 gram. There have been several statements that basically, but of course, the RNA mass, of course, is 10 to the power minus 18 gram. But that is inside that particular virus. Now, assuming mean kinetic energy of roughly of the order of kT, right? If kT is roughly the velocity comes out to be coronavirus particle, if it is there in the air, it is 9 centimeters per second. And then corresponding de Broglie wavelength, if I calculate, the de Broglie wavelength corresponds to 0.00007 angstrom, which is much smaller than 129 nanometers. So therefore, coronavirus also obeys classical laws as far as the transmission from one place to another place is concerned. And that, of course, these days we know coronavirus has revolutionized our way of living. And anyway, that is besides the point. There is a role in philosophy. Quantum mechanics as or uncertainty principle has a role in philosophy. Laplace wrote a book as far as celestial mechanics and is presented to Napoleon. Napoleon glanced through that particular book and asked him, why there is no mention of God in that particular book? Laplace then replied that he did not feel it necessary to include God in that particular thing because God is not necessary. So anyway, that is basically the idea. Laplacian dream is basically that you can do calculation. Everything is deterministic. All laws of physics are deterministic in origin. So therefore, entire thing can be deterministic. But of course, statistical mechanics, because we cannot do that particular thing. But that is the Laplacian dream. Laplacian dream basically says everything in the world is deterministic. But as soon as the uncertainty principle enters, uncertainty principle basically says that nothing is certain. Everything is uncertain. Everything in the life is uncertain. Everything is uncertain. Not only that, Einstein added principle of locality. As far as because Einstein gave the general theory of relativity, and he talked about that particular thing, and that unlocality is also gone because of quantum mechanics. Right? There are many aspects to be discussed as far as the philosophy is concerned, the consciousness and so on and so forth. But so far we don't have that much amount of time to talk about that particular thing. In classical physics, there is unity. In quantum mechanics, that is replaced by duality. And Bohr was the first to identify this feature. He termed it complementarity. So that is basically what. Now, resonance particles in particle physics have lifetime related to width of the particle in the experiment. Another small thing that one has to understand, that as far as the molecular energy information transfer is concerned in our body, information is transferred from one, for a DNA molecule stores the information, and it is transferred by DNA to RNA, and RNA goes to mitochondria in order to construct proteins. So in order to construct protein, information has to get transferred from DNA to RNA and RNA to mitochondria. Now that information transfer must be done by a large molecule, because if that information is transferred by a small molecule, quantum fluctuation would produce large number of fluctuations, and that would basically increase the number of mutations, and that would increase the evolution rate. Whether that is good or bad, I don't know. But anyway, as far as the life is concerned, the information transferred is always by very large molecule. Now, this is something which Professor Joshi would have talked about, that is Hawking radiation. Hawking radiation is also because of uncertainty principle, that around singularity, you can produce, because of quantum fluctuation, electron-hole pairs. One particle goes inside, other particle goes away, and that basically produces radiation somewhere else, and that is basically Hawking radiation. And that is more or less all that I wanted to talk about. I thank you very much for listening to me.
Sir, there are some questions, and you can see them in your Q&A tab. You can choose some questions to answer, sir. Or shall I do it for you?
Well, you can give an insight on entropy information theory of explaining black hole. Now, I do the first question that is there in explaining black hole. Professor Joshi would have talked about that particular thing. Does parallel universes really exist? Now, these are the theories. Whether they exist or not, it is a viewpoint that one particular person takes. Whether that really exists or do not exist, that is another viewpoint of the quantum mechanics. I don't know. Many things that are there are not my. That is not.
Sir, I think. Okay, sir. Sir, I actually dismissed all the other questions, but I'll read these questions for you now, which have come in your talk. Okay. What is the physical interpretation about Schwarz inequality? Does it have any relation with uncertainty?
Schwarz inequality and uncertainty principle. No, actually, that is not related. Schwarz inequality is related to something else. That is not related to this particular thing.
Okay. Now another question which is asked is, are there any other conjugate quantities other than position, momentum, energy, time, and J theta?
Well, these are the only three things that are there as far as the conjugate parameters are concerned. If we consider many dimensional, as in quantum cosmology, one talks about, or particle physics, one talks about many dimensions, that as far as the strings are concerned, the strings are dimensionality is much more than 10 or something. Then in that case, there will be many more conjugate variables in that particular theory. Okay. But as far as ordinary things are concerned, we talked only about the position, momentum, time, energy, and angle and angular momentum.
Okay. Sir, another question. There are two similar questions. I will read out one of them. In double slit experiment, the understanding that a single electron is present at both the slits as a result of probability, and it is just a statement. That's what he's writing. How can this statement or understanding explain the interference pattern by a single electron?
Well, interference, as far as the single electron is concerned, single electron, whenever it falls on the screen, gives you one particular spot. And that particular spot does not tell you whether there is an interference or not. But that spot normally occurs wherever the interference pattern maximum would occur. And if the number of electrons or number of photons keep on increasing, they will fall more or less at the place where the slit, more or less where the maximum of the intensity should occur. And then as the number of photons and number of electrons goes on increasing, as Tonomura's experiment actually shown, that slowly and slowly the interference patterns will develop. So as far as one individual electron is concerned, whether that gives rise to uncertainty or the interference pattern is, of course, one electron cannot show you interference pattern. In order to see interference pattern, you must have many electrons or many photons. And that is the reason why a single, but of course, you realize that the interference pattern is produced, definitely produced. And that means that an individual, according to as the Dirac basically says, an electron interferes with itself. And otherwise, you cannot never obtain interference pattern with many electrons also. So therefore, it is basically a situation that single electron also produces interference pattern.
Okay. Okay. Sir, another question is by Manojit Chatterjee. He says that if hydrogen is in first excited state, then it can only release an exact amount of energy. The difference between the energy of n equal to 2 and n equal to 1 state is exactly same every time. Where is the uncertainty in energy in all these things?
Well, it is not, as far as the energy is concerned, whenever the energy is given out, so transition time is basically involved. Transition time is involved. So therefore the transition time is uncertain, and therefore there is uncertainty. So that is the reason now the photons that come out from various hydrogen atoms, if you take the spectroscopic photograph, then you realize that all photons do not have the exactly same wavelength. They may have different wavelengths, and that is why there is a line width. The line width is not an experimental error. It is actually really present there. And that line width basically means the energy of the n is equal to 2 state and energy equal to 1 state are not exactly known. So therefore, whenever the energy transfer takes place or the transition takes place, the energy that is given out to the photon is not exact, it is uncertain. Okay.
Hello.
Sir, there is another question. Is time travel possible with the help of quantum mechanics in future?
Time travel is possible or not? Time travel is time travel. No, that is another question that Professor Joshi would basically answer very nicely. Whether time travel is possible or not. There are many novels, many science fictions that are written for the time travel, and that of course there are fallacies that are present there. That if I go back and kill somebody and then later on come back here, whether that is possible or not. These are fallacies that are there in time travel. Whether time travel is possible or not, that is clear. Of course, that is basically, as far as the time cone is concerned, in curvilinear geometry, time cone can have different directions, and therefore time travel is possible in that particular case.
Okay, sir. I think we will take a last question, which is again probably between both the talks. Does wormholes have anything to do with uncertainty?
I don't know. I don't know about that particular part.
Okay, fine. So I think we can close for today.
Yes.
Whatever other questions we have, we will be sending it to you, sir, later.
Okay, okay.
Yeah. Thank you, sir. Tushar bhai.
Yes, sir.
Thank you, sir. Thank you.
Thank you very much, Potbhare sir, for your wonderful and very interesting talks. Thank you very much, sir.
Okay.
Dear friends, today I am very happy to inform you that our General Secretary of Gujarat Science Academy is present with us, Professor Nayan Jain. Professor Nayan Jain is a professor and head of the Department of Life Sciences, a coordinator of Department of Biochemistry. He is a director of MSc Food Sciences of Gujarat University. Dear friend, he is a molecular cell biologist and a pioneer researcher, and he's a coordinator of central assessment of our medical facility, and he's actively involved in the IQAC cell of our Gujarat University. Dear friend, he is a multifaceted personality and asset of our Gujarat University. With this brief introduction, I will request Professor Nayan Jain to conclude this session and propose the vote of thanks. Over to Nayan Jain, sir. Thank you, sir.
Thank you, Tushar Pandya-ji. Really is a great day for me. Being a biologist, I have the privilege to hear the important quantum mechanics and their theories. As Dr. Potbhare has said, there is no compartment, no isolation. We believe in compartment as we don't understand the limitation anything, but these are interconnected. So really move us, dear eminent personalities, great professors, scientists, and distinguished delegates of this webinar. Really, it's pleasure and privilege for me to propose vote of thanks for this eminent speaker on behalf of Gujarat Science Academy, Indian Physical Teacher Association of Teachers, Indian Physics Association of Baroda Chapter, Applied Physics Department, Faculty of Technology, MSU University, and with the technical support of Essence Tech. Today is the second day of the webinar with the two important lectures given by first, that is the third lecture by the Dr. Pankaj Joshi, Provost Charusek. Really has taken us to the quantum mechanics, started initially with the strain and limitation of quantum mechanics and leading to the quantum gravity. Really has impressed me most about the emphasizing the fundamentals of forces of nature and correlated the pattern of curvature. His important discussion about the massive collapse of massive stars and formation of black holes and correlated with the naked singularities really is impressed me most also. Naturally, this is also as an interesting talk. The interesting questions were answered with him. There were good number of questions. Naturally, he is able to answer good number with the explanatory interest and naturally focus on the singularity. The fourth lecture, Uncertainty Principle by the Professor V.N. Potbhare. Naturally, that is the really moved me most, which made me understanding about the determination of molecules, what we come across. Now, naturally, the uncertainty started with the principles and discoveries in the sequence of history about the one by one, and naturally is intercorrelated and interconnected them, saying that nothing is compartment. We understand in compartment due to our limitation, but naturally they are the interconnected. He continued the quantum revolutions, discussed elaborately the radiations, their characteristics, and its application to the principally understanding the mechanism. Naturally, he has come that the quantum mechanism, it can be go in the line of duality and complementary. He has emphasized the movement of the molecules in the cell from the cytoplasm, the mitochondria, and nucleus very lightly and very emphasizingly. That is also impressed me more. He has also discussed that these principles and radiation movement has may be related with the transmission of coronavirus. Thank you so much, sir. Really, this lectures has given us the hope that whatever the webinar we are conducting really is food for all the attending participants. Thank you both of sir. Thank you.